Hello and welcome to the lecture series on applied thermodynamics. In today's lecture we are going to look at a reheat method, and based on this method we will take up one numerical problem. Just before we proceed with reheat method, let us recall some of the methods which we have discussed in the last class. So in the last class we have basically looked at number of methods in order to increase the thermal efficiency of a steam power plant. So we understood that the ideal cycle for the steam power plant is Rankine cycle, that is ideal cycle fitting for steam power plant. And we identified that there are some three methods which are basically been proposed in order to increase the thermal efficiency. And the idea behind improving the thermal efficiency was in order to obtain some benefit in terms of reducing the cost of operation, that is in terms of saving the cost on the fuel procurement. And we saw that in the world most of the power plant are working on thermal source. So steam power plant is largely employed, and that is a base power plant throughout the world which is supplying huge amount of electric power throughout the world. Therefore a small increase in thermal efficiency will save huge amount of money in terms of fuel procurement. Therefore we understood that in order to increase the thermal efficiency of Rankine cycle, the focus is primarily on average temperature at which heat is added to the working fluid in the boiler, and decreasing the average temperature of the working fluid at which heat is rejected in the condenser. So the focus is either to increase the average temperature of heat addition at the boiler end, or decrease the temperature at which heat is rejected at the condenser. So this is the basic bottom line around which these improvement of thermal efficiency is possible. So with this in focus, we have identified some three methods. Method number one was lowering the condenser pressure on a TS plot. If we lower the condenser pressure, then we understood that amount of heat that is rejected can be saved, and that will obviously help in improving the thermal efficiency. But however, we also understood that there is a limit on setting the or operating the condenser pressure because reducing the condenser pressure beyond certain limit can lead to a problem of leading to some vacuum, and then air bubbles may be trapped, air leakage, and also reducing the temperature in the condenser may lead to a problem of moisture content during the final expansion of the steam inside the turbine. Therefore the turbine blades may encounter moisture towards the final stages, and that can erode the blades of the turbine. Therefore the pressure of the condenser is largely dictated by the saturation temperature pressure, in other words, in correspondence with the cooling medium which is seen in the condenser. Therefore it cannot be lower than the saturation pressure corresponding to the temperature of the cooling medium. So that is important. Moving to the next method was superheating the steam to a very high temperatures. So one can superheat the steam, and one can increase the temperature of the working fluid. That will obviously add area on the TS plot, and also it will help in reducing the quality of the mixture, and but however we found that increasing the temperature of the working fluid beyond certain temperature limit is critical. So the maximum temperature is around 620 degrees Celsius. So if temperature has to be increased more than this, one has to come up with some innovation in terms of material research so that the blades can take up that amount of temperature. Therefore it is purely material consideration point of view, the temperature is limited to 620 degrees Celsius. Now the last one was increasing the boiler pressure. So we have a TS plot here, and we have the normal pressure of the boiler, which is shown here from 2 to 3. Now proposing the third method, which was increasing the boiler pressure, which obviously increased the corresponding saturation temperature, so we can get a twin benefit of increasing the pressure along with the temperature. So that was the idea here. Therefore we have a new curve here, boiler pressure 2' to 3'. So we can see that if we increase the pressure of the boiler, the area on the right hand side is decreasing because the cycle is shifting towards the left side. On the left side we can see this much area has been added, along with that there is a sensible heat also been added area. So therefore the heat area that is getting increased is much higher as compared to the decrease in the area. So this method is attractive, but when we look at the quality point of view, dryness fraction, we see that the state point 4 is getting reduced to 4', thereby the quality is getting dropped. So that is not attractive, that is not desirable. Therefore in order to take the advantage of increasing the boiler pressure without compromising in the dryness fraction, a process called as a reheat is proposed. In case of reheat, in the turbine, when the fluid is expanded from 3', it will be expanded partially in high pressure turbine, and then before it encounters the saturated vapor curve, the fluid will be directed to the boiler and it will get again heated up at a intermediate pressure, and this intermediate pressure is called as a reheat pressure, which is shown here with the arrow mark. So along this curve the pressure is constant, so it passes from 2 to 3. So the reheat process takes place from point over here to point 3. So this is where heat is added at an intermediate pressure. So this point is now taken up to a maximum allowable temperature here, whatever it is, and then at point number 3 the fluid is again subjected to lower pressure turbine. So we have again the secondary expansion here happening from 3 to 4. So we had first expansion happening from 3' to this point, and the second expansion happening from 3 to 4. So we have a total turbine work is a sum of work which is in the first turbine, that is a high pressure turbine, plus the work that is extracted in the second turbine. And then we have the regular cycle here. From 4 to 1 is a heat rejection process, and 1 to 2' is a pump work. Again from 2' to 3' is the heat addition in the boiler. So the process continues like this. So we are now looking at the arrangement of the entire reheat cycle here. So we can see high pressure turbine, the fluid is expanded here to partially to some extent, and then it is again directed to boiler, gets reheated at a intermediate pressure, which we can see here from 2 to 2', and then the steam is subjected to the low pressure turbine. So we have the expansion happening from 2' to 3. So 2' to 3 is the next expansion happening, and then the fluid is subjected to the heat rejection process in the condenser, that is from 3 to 4, and point number 4 is a saturated liquid. So we have exactly on the saturated liquid curve, and from 4 to 4 dash we have a high pressure work input. Isentropically the work is added, so compression process is happening here, and from 4 dash to 1 dash again there is a sensible there is a heat that is added to the working fluid. So we have here the process 4 dash to 5, which is a heat added in terms of sensible heat, and from 5 to 1 dash is a heat that is added in the boiler. So this is the arrangement of reheat cycle along with TS plot. With this now we can figure out what is the heat added. So now we can see that the heat is added into the cycle in two stages. One is the heat that is added in the boiler, that is from H1 dash to 4 dash, that will be the boiler heat addition, and then we have a reheat heat addition that is from H2 dash to 2. Therefore we have the total heat as heat added in the boiler plus heat added in the reheat process. Now looking at the work, again work also we have we see that it is happening in the two stages. Therefore total work is sum of work that is done in the turbine 1, high pressure turbine, plus the work that is done in the turbine 2, that is a low pressure turbine. So we can write here total work done is equal to work done in the turbine 1, that is from H1 dash to H2, plus work done in the turbine 2, that is H2 dash minus H3. So these are the variations compared to the simple power plant Rankine cycle. Now moving further, let us now write down the thermal efficiency equation. So we have thermal efficiency equation as net work output divided by the heat input. So since it is a net work output, so we have turbine work on one side and then we have pump work on one side. When we from the total work done by the turbine, when we deduct the pump work, we are going to arrive at net work done. Therefore now let us look at the final equation. So we have turbine work here, the work that is done in the stage 1 turbine, that is high pressure turbine, plus the work that is done in the low pressure turbine, minus the pump work which is given as H4 minus H1. So divided by the total heat input. The total heat input again we have, it is happening in two stages, that is H1 minus H4 dash, H1 minus H4 dash, plus the heat that is added in the heat, that is H2 dash minus H2, H2 dash minus H2. So this is the final equation for the thermal efficiency in case of reheat based cycle or reheat process, considering network output. Now with this we are in a position to take up one numerical problem on this concept. Let us now proceed with the numerical problem. So we have a problem here. An ideal Rankine cycle with reheat is designed to operate according to the following specifications. So we have an ideal Rankine cycle, and this ideal Rankine cycle is now modified for to represent a reheat cycle, and then it is operating with the below specifications. Pressure of steam at high pressure turbine is 200 bar. So therefore we see that the boiler pressure is around 200 bar, which comes to 20,000 kilopascal in terms of kilopascal unit. And then we have a temperature of the steam at high pressure turbine inlet is 550 degrees Celsius. Therefore we have P1, which is a boiler pressure. We denote it as a P1. P1 is 200 bar, and the corresponding temperature is T1, which is 550 degrees Celsius. Then we have temperature of the steam at the end of reheat. That means at state point 2 they have given us T2 is equal to 550 degrees Celsius at the end of reheat. So that means it is actually T3. T3 is 550 degrees Celsius. And then so we don't see what is the corresponding reheat pressure they have given. It is not given. We have to work it out. The pressure of steam at a turbine exit is 0.15 bar, which is in terms of kilopascal it comes to 15 kilopascal. So we have a quality also been given, which is 0.94, and we have a condenser pressure which is given as 0.15 bar. They asked to find out the ratio of pump work to the turbine work. It's a ratio. And then they asked us to find out the heat rejection ratio, heat rejection to that of total heat and supplied, and then we have the final parameter, that is cycle efficiency. So now let us proceed looking at the TS plot for the given problem. So here we have a TS plot, we have a saturation dome, and we have state point number 1. The state point 1 to 2 signifies the turbine work, which is isentropic expansion process. Therefore one can extend this line further and cut the x-axis. Since it is isentropic, we can write as S1 is equal to S2, and this data is very important so that we can find out what is the reheat pressure. And then we have next reheating process happening from state point 2 to state point 3, and at state point 3 they have given us it is at 550 degrees Celsius. Therefore state point 1 and 3, they are lying on the same horizontal line. So we note that state point 2 and state point 3, they are operating on the same common pressure, that is reheat pressure, which we don't know, we have to work it out. From state point 3 to state point 4, again we have expansion work done by the turbine. So therefore this is again isentropic expansion process. One can extend the line and cut the x-axis. Therefore we can write S3 is equal to S4. Why? Because it is isentropic expansion process. Therefore the entropy has to remain constant. And then from state point 4 to 5 we have a heat rejection process in the condenser, and from state point 5 to 6 is the pump work input, and from state point 6 to 1 is the heat added in the boiler. So this is about the cycle. Now let us list the given data. So in the given data we have the boiler pressure as 200 bar, and the temperature at which the steam is supplied to the turbine at state point 1 is 550 degrees Celsius, and the temperature of the after end of reheat is 550 degrees Celsius. Therefore this T3 is equal to 550 degrees Celsius, and they have given us the condenser pressure, which we denoting as a P2, which corresponds to condenser pressure, which is shown here in this line, so which is 0.15 bar. And then we have the quality, that is X4. This is supposed to be written as X4, which is 0.94. Now let us write the equations for the parameters to be worked out. So they asked us to find out the work ratio, the pump work divided by the turbine work, and the heat ratio is heat rejected to the total heat input, and cycle efficiency is a net work output divided by the total heat supplied. So these are the parameters that has to be worked out. So now if we look into all these parameters, that is a work ratio, heat ratio, and cycle efficiency, all these has to be worked out in terms of enthalpies. These are expressed in terms of enthalpies. Therefore from the TS plot across each state points we have to work out what is the enthalpy. So based on the given data, at state point 1 we know pressure P1 and we know temperature T1. Therefore referring to the data table we have to find in which phase it is, so that we know which is the right table to be referred, and we have to note the enthalpy at the state point 1. Similarly at state point 2 also we have to find out the enthalpy. State point 3 also we have to find enthalpy. 4, 5 and 6 likewise. So once we find all the enthalpies, and we can substitute those enthalpies in the given equations and find out the unknown parameters. So that is the exercise we are going to follow now. Let us now proceed with state point 1. In state point 1 we know two datas. We know the boiler pressure, which is 200 bar, and we know the temperature at which the steam is supplied to that of turbine 1. So that is 550 degrees Celsius. Now with this data we have to find out the enthalpy, that is H1, which is a question mark. To find out H1 we need to know which table to refer. Therefore we have to first find out in which phase it is. So we know the guidelines in one of the earlier classes we have studied. If the given temperature is greater than the saturation temperature, then it is in superheated phase. Therefore we have to refer to the superheated tables. If the given temperature is less than the saturation temperature, then it is in the subcooled liquid region. One I have to refer to the subcooled liquid data table to find out the required parameters. If it is in terms of pressure, then guidelines has to be followed and addition has to be made. So now let us look into the data table. For a pressure of 200 bar, let us look at the saturation temperature so that we can compare the given temperature with the saturation temperature to arrive at a decision to which table to refer to. So let us now refer to the data table for a pressure of 200 bar. So here we have a data table, table number A1, and in the first column we have the list of pressures. Therefore this is a pressure entry method or pressure entry tables, and these are the corresponding parameters, and our focus is on 200 bar pressure. So therefore we now proceed from top to down as we go step by step, and we arrive at a pressure of 150 bar and then 180 bar, and then we have 200 bar. So at 200 bar, next column is the saturation temperature. So for a pressure of 200 bar, the corresponding saturation temperature for 200 bar is 365.71 degrees Celsius. Therefore now we can go back to the tables, back to the problem. So now the given temperature is 550 degrees Celsius, but whereas the saturation temperature at 200 bar was 300 and some temperature, that is 365.71 degrees Celsius. So when we compare the given temperature with the saturation temperature at 200 bar pressure, we see that the given temperature is greater than that of saturation temperature. Therefore according to our guidelines, this equation satisfies a criteria so that the phase is superheated. Therefore we have to refer to superheated tables, and then for a pressure of 200 bar and for a temperature of 550 degrees Celsius, we have to make a note of enthalpy. Now let us refer to the superheated tables corresponding to this data. So here we are referring to a superheated tables, table number A3, page number 21. We see on the first column we have a list of pressures, and in bracket whatever we have is a saturation temperature corresponding to this pressure, and then we see that 200 bar pressure is shown here because the state point 1 is at 200 bar and temperature is 550 degrees Celsius. Therefore we are now focusing at this point 200 bar pressure, and the corresponding saturation temperature is 365.7 degrees Celsius. So here we have three parameters, working fluid parameters. One is a specific volume, enthalpy and entropy. So the first row corresponds to specific volume data, second row corresponds to enthalpy data, and the third row corresponds to entropy data. So we have here list of temperatures, temperature 200, 250, 300, 350, but our target is to refer to 550 degrees Celsius. Let us proceed. So we are now at 500 degrees Celsius, and the next temperature is 600 degrees Celsius, but what we are looking for is 550 degrees. Therefore we don't have the required temperature data here, therefore that temperature data is missing. So, and we understand that this 550 is exactly a midpoint between 500 to 600. So one can take the average values directly, or one can interpolate to find out the enthalpy. So our focus is here on this box. So we are referring to the enthalpy, that is a second row. For a 500 pressure, the corresponding enthalpy is 3241.1 kilojoule per kg. Similarly, for 600 degrees Celsius the corresponding enthalpy is 3535.5 kilojoule per kg, and for 550 degrees Celsius we don't have, it is a X. Therefore we can formulate here so that we can interpolate. So for 500 degrees Celsius the corresponding enthalpy is shown here. For 550 degrees Celsius it is unknown, therefore it is been substituted as X, and for 600 degrees Celsius we have the corresponding enthalpy noted from the following box. Therefore we are going to now interpolate this, that is 600 minus 500 divided by 550 minus 500, that will be equal to 3535.5 minus 3241.1 divided by X minus 3241.1. So that is shown here. So from this equation the only unknown is X, therefore we rearrange the equation and work out the value of X. So this X represents enthalpy. Therefore once we work out, we are going to arrive at 3388.3 kilojoule per kg, and this value corresponds to enthalpy at state point 1. So please remember that this H1 is at 200 bar pressure and 550 degrees Celsius. Likewise we need even the entropy value also here. So for that we have to refer to the entropy data on the last column, and then we get for 500 degrees Celsius the corresponding entropy is 6.1456 kilojoule per kg Kelvin. Similarly for 600 degrees Celsius we have the corresponding entropy value as 6.5043 kilojoule per kg Kelvin, and for 550 degrees Celsius we don't have the entropy, which is taken as X. Therefore following the similar procedure what we did for the enthalpy, we follow that for the entropy as well. For 500 degrees Celsius we have the entropy from the above box, we note it down, and for 550 degrees Celsius it is unknown, therefore it is X. For 600 degrees Celsius we have picked up the value from the above box as shown. Therefore now we are going to formulate this 600 minus 500 divided by 550 minus 500, that will be equal to 6.5043 minus 6.1456 kilojoule per kg Kelvin divided by X minus 6.1456. So I have now shown that here, and the only unknown here is X. Therefore we rearrange this equation and then we find the X, and X works out to be 6.3249 kilojoule per kg Kelvin. So this is the value of entropy at state point 1. Therefore now we could able to find out the enthalpy at state point 1 and entropy at state point 1. So let us now note this in our problem. So let's now proceed noting down. So we have referred to the table A3, this is related to state point 1, and 550 data was not available directly, therefore we interpolated the value for the enthalpy and we got as shown. Similarly, similar procedure we followed for entropy as well. For 550 degrees Celsius data was not available, therefore we interpolated, and then upon solving we arrived at entropy value at state point 1 as 6.3249 kilojoule per kg Kelvin. So with this we are done with enthalpy at state point 1 and the entropy at state point 1. Let us now proceed with state point 2. So from the TS plot we understand that after knowing the value of enthalpy 1 and then entropy 1, we see that state point 2 is isentropic expansion, therefore it is the entropy is constant here, therefore we can use S1 is equal to S2 in order to find out the enthalpy at state point 2. So knowing we have only one data here, that is S2 value, because S2 is equal to S1, and we also know that state point 2 is approaching closer to that of saturated liquid curve. So that means we don't know what is intermittent pressure, but we know that the entropy at state point 2 is closer to that of saturated vapor region or vapor point, trisaturated. Therefore we have to go on searching the table holding the value of S2. S2 is equal to S1 here in this case, and see where exactly it will coincide, and that particular coincident point, once we refer to the pressure column, we will get the required intermediate pressure, which is called as a reheat pressure. So this is the process we are going to follow now to find out the intermediate pressure, so that with the known pressure and the entropy one can find out what is the enthalpy at state point 2. So let us now proceed. So we don't know H2 value, and we also don't know what is the temperature at state point 2. Therefore we don't know what is the value of intermediate pressure. We only know the data corresponding to S1, and since state point 1 to state point 2 is a isentropic expansion, therefore S1 will be equal to S2. Therefore we are going to search the tables holding the S1 point. So now let us look into the data and see where exactly the S1 is equal to S2 is going to coincide. So here we are having tables, table number A1, and now we are referring to the table, and we are focusing on the last column, which is pertaining to dry saturated condition of entropy, and our target is here holding the S1, because S1 is equal to S2, 6.3249. we have to see where exactly we are going to find this data from the saturated vapor curve line, which is represented here as SG. So let us now proceed one by one. So we have 6.89 kilojoule per kg Kelvin. Proceed further because that is not matching the given entropy value. We'll proceed further, and then we come across 6.37, which is close to this value. Let us proceed further and say this is 6.35. we are much more closer. Let's now proceed further, and we come at 6.33, and then the next point is 6.25. so now only looking at these 2 points, the closer entropy value to the S1 is 6.3377. so this is closer to that of the S2 value. Remember that S1 is equal to S2 here. Therefore we see that the state point 2 entropy is coinciding with this data value. Let us now proceed along the horizontal line so that we can note the corresponding pressure at which this entropy is existing, and we see that the pressure is 20 bar. So this becomes the intermediate pressure. We call this as a reheat pressure. Therefore, since the state point is exactly on the dry saturated curve, therefore the enthalpy will be SG value. So we will look at the SG value column, and then we trace that the H2 will be 2797.2 kilojoule per kg. Therefore with this understanding we can write S1 is equal to S2 because it is isentropic expansion, and the S2 is closer to SG value from this data table. So we can, based on that, we can write the equation as shown here. So now we are in a comfortable position, that because we know what is H2 value, and we also know S2 value because S1 is equal to S2. So now let us proceed to the problem. So now we found out that the read pressure was 20 bar, and the corresponding saturation temperature will be T2, which is 212 degrees Celsius. And with this, let us now proceed with state point number 3. To proceed with state point number 3, again at this state point number 3, we note that the pressure is a reheat pressure, that is 20 bar, and the corresponding temperature is 550 degrees Celsius. Therefore at state point 3 we have a reheat pressure and the given temperature. So referring to these two, again we have to refer to the data table. So let us look at the data table. So here we have a data table, and for a pressure of 20 bar, we see that the corresponding temperature is 212.37 saturation temperature, but the given temperature was 550. Therefore the given temperature is greater than the saturation temperature. That means we have to refer to the superheated tables. So one has to refer to the superheated tables at 20 bar, and then one can note down the corresponding enthalpy value. So once we refer to the superheated table corresponding to 20 bar and 550 degrees Celsius, 550 degrees Celsius may not be available straightforward. We may have to interpolate, just like the procedure been followed earlier, and we can find out H3 value as 3758.25 kilojoule per kg. So we see that the given temperature is greater than saturation temperature, therefore it is in superheated vapor region. So we had to refer to superheated tables, and 550 degrees Celsius corresponding data was not available. We had to interpolate and get the value. And we also proceed to find out the entropy at this point, state point. Let us now continue the problem at state point 3, referring to the superheated table and corresponding entropy values, and straightforward the value is not available. Therefore we are going to interpolate for the entropy, and then we arrive at entropy at state point 3 as 7.56725 kilojoule per kg Kelvin. So now we are done with finding out the enthalpy and entropy at state point 3. Now we'll proceed to find out the enthalpy at state point 4. Now let us look at the TS plot. We are now ready with state point 1 data, state point 2 data, state point 3 data. Now we have to find out the enthalpy at state point 4. To find out the enthalpy at state point 4, we have to first find out whether this point is within the saturation dome or outside the saturation dome. If it is within the saturation dome, then we have to apply the equation that applicable to two-phase region, and then we have to find out the enthalpy. Since they have given to us the quality, that is a dryness fraction, that is 94%, that shows that it is inside the dome, inside the saturation dome. And the other thing is, since it is isentropic expansion, we can write as S3 is equal to S4. So we have now the two datas with us. One is the dryness fraction, the other one is entropy value. And we also know the condenser pressure, that is 15 kilopascal or 0.15 bar. So we have three known datas, therefore finding the enthalpy is straightforward. So we know that P2 is 0.15 bar and dryness fraction is given to us, and S3 is equal to S4 because it is isentropic expansion pump work in the low pressure turbine work, not pump work. So with this data we are going to find out the enthalpy. So since the point is within the saturation dome, we have to apply the equations pertaining to two-phase region. Therefore we can write H4 is equal to HF plus X into HFG. So we have the equation here, and H4 is unknown to us, but we know HF pertaining to 15 bar, 0.15 bar, that is 226, and then X4 is 0.94, and HFG we have to note from the data table corresponding to 0.15 bar, and we substitute all those datas into this equation, and then we find out H4 as 2456.8 kilojoule per kg. Now with this we are done with finding the enthalpy at state point 4. Now at state point 5, from the TS plot we know that state point 5 is on the saturated liquid curve, therefore HF will signify as H5. So this is straightforward. So we have H5 is equal to HF at a pressure of 0.15 bar, which is noted as 226 kilojoule per kg, which is similar to the above one. Now proceeding with state point 6, we know that state point 6 can be worked out the corresponding enthalpy based upon the pump work, because process from 5 to 6 is a pump work from the TS plot. Therefore we have H6 minus H5 is equal to V into dP. So we apply that equation, dH is equal to V into dP. H6 minus H5 is equal to Vf pertaining to 0.15 bar and we have the boiler pressure minus the condenser pressure. So there is no reheat pressure here, please recall, because state point 6 refers to the boiler pressure and state point 5 refers to the condenser pressure. So we have to note down the corresponding pressure values. So we are going to substitute the data. For H5 we are going to take minus H5 to the other side of the equation, so this becomes positive, plus Vf from the data table we note down, and pressure is substituted in terms of kilopascal here, that comes to 20 kilopascal, which is 200 bar, and then the condenser pressure is 0.15 bar, which is substituted here in terms of kilopascal, that is 15 kilopascal, and we get enthalpy at state point 6 as 246.26 kilojoule per kg. So with this, friends, we have now worked out all the relevant enthalpies across different state points on the TS plot. Let us now list all these enthalpies as a chart. So we have all the enthalpies and the corresponding entropy values as well. So from the TS plot, all across all the state point, that is state point 1, 2, 3, 4, 5, 6, we have the enthalpies, and at the state point 1 we have the corresponding entropy values. Please note that state point 1 and state point 2 was isentropic expansion process in the high pressure turbine, therefore entropy value is similar. And we also note that state point 3 and state point 4 is the low pressure turbine work, therefore these two entropy values are constant, they are similar. Now with this, let us now work out what is the work ratio. So we have the equation work ratio from the TS plot. So work ratio is given as a ratio of pump work to that of turbine work. So pump work we can see here, that is H6 minus H5. So in the numerator we have pump work H6 minus H5, and in the denominator we have turbine work. So turbine work is happening in two stages. One is in the high pressure turbine, the other one is in the low pressure turbine. Therefore we have H1 minus H2, which corresponds to turbine 1 work, and H3 minus H4 correspond to turbine 2 work. Therefore we have the enthalpies which we worked out earlier. We can substitute those datas into this following equation and get the value of work ratio as 1.18%. So this 1.18% signifies that from the turbine work, whatever the work is produced, out of that 1.18% is being used up by the pump work. So it's a very small magnitude as compared to that of turbine work. Therefore usually in most of the problems pump work is neglected for this reason. Now let us proceed with working out the second parameter, that is heat ratio. We have a heat ratio which is given as heat rejected to that of total heat. Again, let us now look at the TS plot. We have the heat rejected is H4 minus H5. In the numerator we have H4 minus H5 divided by the heat addition, total heat addition, which is happening partly in the boiler and partly in the reheat process. Therefore Q primary refers to the heat added in the boiler, which is H1 minus H6, which is given here H1 minus H6, plus we have a reheat, the temperature that is added to the working fluid, that is H3 minus H2, H3 minus H2. Now from the chart we already worked out the enthalpies. Let us plug in those corresponding values of enthalpies into the equation, and the value will be 56.86%. So this percentage heat rejection shows that out of the total heat supplied, around 56.86 amount of heat is being rejected out. That is a huge amount of heat that is being left out into the ambient. So there is a huge scope to utilize this heat, and therefore some specialized applications like cogenerations are attractive from looking at the possibility of saving the heat. Now let us proceed with the third ratio, that is the cycle efficiency. So we have network output in the numerator, and denominator is the heat that is supplied. So therefore we have the net work output as a turbine work minus the pump work divided by the heat supplied partly in the boiler, partly in the reheat process. Therefore we can substitute the enthalpies into this equation and they get the value of cyclic thermal efficiency of the cycle as 43.13%. So this value indicates that out of the total amount of heat that is supplied into the plant, 43.13% being effectively used in order to convert that into work output. So there is a huge amount of heat that is not being converted into work. So there is a huge scope of saving the heat energy. So friends, with this we are now coming to the end of this lecture. I thank you for your attention. So for the more details on this topic you can refer to the following textbooks. Thank you for your attention.